All right. Well, it is 3:30. I guess we can go ahead and get started. Oh, sorry, I've not turned off the, hold on a second. Captions. Captions. Okay. All right, we are good to go. Okay, yeah, wow, cool. Looks like some people have some really interesting spring break plans. I'm getting some private messages here as well. So I don't know about you guys, but I think yeah. The week before spring break, I think my energy is not the highest that it usually is throughout the year. So I don't know about you guys, but yeah, usually your professors are definitely, looking forward to the spring break, probably as much as you guys are. So yeah, what we're gonna do this week is wrap up with our discussion on the DB scan algorithm. Um, Today, maybe if we have time, we might move on to fuzzy C-means, which is going to basically be a fuzzy clustering extension of the k-means clustering algorithm. And yeah, I think that basically is it. I will release another homework assignment Friday night, but you will get 2 weeks to work on it. So I don't want you to just be working over the break. Taking an ample break is good for everybody, basically. So one additional thing that I wanted to mention. So I think probably a lot of you here are statistics majors, so maybe you've already heard about this. But if you do plan to work in the field of data science, not just taking a lot of classes, but also, engaging in, competitions as well as internships and just generally engaging in experiences in which you can, really get your hands dirty. Playing around with data sets, pursuing some sort of a research goal can be a, very invaluable experience to, learning more about what what it means to be a data scientist, as well as like boosting your resume. So we do have the Datathon with the Illini Statistics Club, which is coming up on March 22nd. So if you're interested in learning more about the Datathon, as well as, getting ideas to what a good Datathon project might look like, we do have a workshop going on in the SIF from 6 to 7 tonight, if that was something that you were interested in. So that's basically, things that I wanted to discuss. Do take note, there was a small typo in the homework assignment, particularly question 1 in the PDF. So I did leave a note about that. So do keep that in mind when you're going through that question. But yeah, I think that's basically it. So yeah, any questions before we get started? Okay. Cool. So we started talking about the DB scan clustering algorithm on Thursday. So there were some additional things that we wanted to talk about before we dig into our application. We're actually using the DB scan clustering algorithm. So one of the things that we talked about is that, number one, the DB scan clustering algorithm is our first density-based clustering algorithm. So every other clustering algorithm that we've discussed so far is a prototype-based clustering algorithm. And, each of these algorithms had sort of a pro and a con, in which that, we had to pre-select the number of clusters that we wanted the given clustering algorithm to return. And so that can be a little bit of a downside if you don't actually know the inherent number of clusters that you're looking for in the given data set. But the positive side is that we introduce all sorts of techniques that gave us clues about how many clusters actually exist in the data set. Now, the downside about dbScan is, maybe you might have a sense as to how many clusters inherently exist in a data set, but dbScan actually does not allow for you to select the number of clusters that it returns. The number of clusters that it returns is simply just what you get. So the two parameters that we are allowed to toggle in dbScan are the min points parameter and our epsilon parameter. So before we move into the application, we want to learn a little bit more about how we might get a sense as to what our dbScan results might look like for different epsilon and min points parameters. And the way that we're going to learn these additional insights is we're going to use these k nearest neighbors distance plots that we discussed on Thursday. So one of the cool things that a k nearest neighbors distance plot can indicate to us, just in general, is, if there is even noise in your data set, to begin with. So we discussed, for instance, if you see in some of these k nearest neighbors distance plots, a large jump in the nearest neighbor for a certain set of points, then that could be an indication that there is, in fact, noise in your data set. And therefore, using the dbScan clustering algorithm to look for that noise might be useful. Now, another thing that we saw, when using these k nearest neighbors plots also, is that it can give you a sense, perhaps, if there are clusters with different densities in your data set. So for instance, if you see like a jump in your k nearest neighbors distance plots to something like this, then that also might be an indication that, for instance, one of your clusters might be less dense, or maybe a subset of your clusters might be less dense than another subset of your cluster. So that's another indication of what a jump in a k nearest neighbors distance plot might indicate. But what we're curious about is, what might these k nearest neighbors distance plots indicate about the number of core points, border points, and min points that you might end up getting in your dbScan algorithm? So regardless of how many min points that you've selected, as long as that min points value is greater than 1, your k nearest neighbors plot, where k is equal to 2 in particular, is able to give us some insights about the nature of some of the points, or the labeled points, in our dbScan algorithm. So for instance, let's just say we plan on running the dbScan algorithm, and we know that we'd like to use a epsilon of 2.5, and our min points is going to be something greater than 1. So we can basically draw, so we can go to our k equals 2 nearest neighbors distance plot. We can basically just draw a horizontal line at that epsilon value here. So we see that 11 points have a nearest neighbor distance that is less than or equal to 2.5. And we see that 2 points have a nearest neighbor distance that is greater than that 2.5. So the question is, what do we know about the nature of these points here, these 2 points here that have a k nearest neighbor distance that is greater than 2.5? So specifically, we're asking, are they going to be a core point? Are they going to be a border point, a noise point, or could they actually technically be anything? So let me open up this poll. I want to see what you guys think. So if we know that a point, given point, we know that its nearest neighbor is greater or more than 2.5 away from it, what does that tell us about that particular point? Okay, so try submit in the next few seconds. Okay, so yeah, most of us say that it has to be a noise point. And yeah, so that is correct. So what this is telling us is that there are actually no points other than the point itself within that particular point's epsilon radius. So what that tells us, provided that the min points value is greater than 1, what that tells us is that it's not going to meet the requirement for being a core point. So for instance, if that min points value was 3, it's not going to meet that requirement. And furthermore, because there are no points within its epsilon radius that are a core point, that also means that that point cannot be a border point either. So therefore, that tells us that that particular point has to be a noise point. Okay. Okay, so what this k equals 2 nearest neighbors plot can indicate to you is a lower bound on the number of noise points your corresponding dbScan algorithm would return. And so let's think about the other scenario. So let's think about what we know about the points in a given data set whose k equals 2 nearest neighbor distance is at most epsilon, or is at most that epsilon value of 2.5. I'm going to launch another poll. So basically, what do we know about these points? Are they a core point? Are they a border point? Are they a noise point? Or could they be all of the above? Okay, so try to submit in the next few seconds. Okay. Yeah, so most of us say that it could actually be all of the above. You're right. So let's just say, for instance, our min points value had been set to 3. So if our nearest neighbor to that particular point is in the epsilon radius, then it's also possible, for instance, that its, second near or its k equals 3 nearest neighbor is also within that epsilon radius. So this would be a scenario in which that particular point could be a core point. All right. And another scenario could be one in which its k equals 2 nearest neighbor point is within that epsilon radius, but it doesn't actually have a third point within that epsilon radius. But let's just say, for instance, the point that was within its epsilon radius was a core point. So in that case, this point could be a border point. Okay. And then similarly, a observation could have a point. It could have its k equals 2 nearest neighbor also within that epsilon radius, but it could be the case that that point is not a core point. So that would be a scenario in which that point that we're considering is a noise point. Okay, so basically, the k equals 2 nearest neighbors distance plot does not actually tell us a whole lot if a given point's nearest neighbor is less than or equal to the given epsilon value. So it could either be a core point, border point, or noise point. Okay, so basically what we just explored is a property that you can actually use for any given set of dbScan parameters that you might be considering. So in particular, if you have selected a given epsilon value, and your min points parameter is anything greater than 1, then what you can do is basically draw that horizontal line in your k equals 2 nearest neighbors plot. And basically any points that has a k equals 2 nearest neighbor value that is larger than that epsilon will be considered a noise point. And then similarly, any set of points whose k equals 2 nearest neighbor value is less than or equal to this epsilon value, like we saw, could either be a noise or a core point, border point, or noise point. Okay. So how a k equals 2 nearest neighbors plot is useful is that basically it can give you a lower bound on the number of dB scan noise points that are detected with your chosen set of parameters. Okay, so if you have a sense as to how many noise points are in your data set, increasing or decreasing this epsilon value in this k equals 2 nearest neighbors plot can give you indications as to the types of, or whether your dB scan algorithm will align with your sense as to how many noise points there actually are. Okay. All right, questions on that? Okay, now furthermore, you can also look up another k nearest neighbors plot, and you can extract some additional insights about what kinds of points your points in your data set will be labeled as. So now in this case, let's just say, for instance, we know that we would like to use a epsilon value of 4. So I'm going to draw a vertical line at epsilon equals 4. And in particular, we'd also like to use a min points value of 3. So the plot, which is going to yield additional insights, is going to be the k nearest neighbors plot that actually corresponds to the min points value that we're considering. We're going to look at this plot here. So k equals 3 nearest neighbors plot. So now the next question is, what do we know? So for instance, we can see that again in this plot, there are 11 points that are, there's going to be 11 points that have its k equals 3 nearest neighbor. At most, with a distance of at most 4. So the question is, what do we know about these particular points? So points such as this. I'm going to launch a poll. So for points whose k equals 3 nearest neighbor is within our epsilon radius of 4, is that point going to be a noise point, a border point, a core point, or could it be all the above? Okay, so try to submit in the next few seconds. So just give me your best guess. Okay. Yeah, so most of us say that particular point whose k equals 3 nearest neighbor is within the epsilon radius of 4 does in fact have to be a core point. So that is going to be the case. Yep. All right. And this is because that particular point is going to have at least 3 observations within its epsilon radius, so therefore it's labeled as a core point. Okay. And finally, let's consider the observations in which we know its k equals 3 nearest neighbor distance is greater than 4. The next question is, what do we know about those points? Okay, so try to submit the next few seconds. Just give me your best guess if you're unsure. Okay. All right, so it looks like we're split between 1 and 4. So actually, it could in fact be a border point or a noise point. But the one thing that we do know is that it cannot be a core point. Otherwise, so for instance, if it did have its, so basically if it's, if it does not have, in our case, 3 nearest neighbors within that epsilon radius, then, it does not meet the parameters or the specifications for being a core point. However, it could be the case, for instance, that it's, while its third or k equals 3 nearest neighbor is not within its epsilon radius of 4, it could in fact actually have its closest nearest neighbor within its epsilon radius. And that point, in fact, could be a core point. So that would make this particular point be a border point. On the other hand, you can also have this scenario in which maybe not its k equals 3 nearest neighbor is within its epsilon radius of 4, but it does have some point. So for instance, its k equals 2 nearest neighbor within its epsilon radius. But if that point is not a core point, for instance, if it's a border point, then that means that point must also be a noise point. So it can't be a core point. And if it's not within so if it doesn't have a core point within its epsilon radius, that means it's a noise point. And similarly, for instance, you could have the scenario in which its k equals 3 nearest neighbor is not within its epsilon radius, and its k equals 2 nearest neighbor is also not within its epsilon radius. And so in that case, that would mean it would have to be a noise point, provided that the min points was greater than 1. So therefore, what that tells us is that that point has to be, or it could be, a border point or noise point. Okay. All right. Just a little bit of color coding here. So yes, any questions on that? Okay. And so basically we can use that same approach for any min points and epsilon value parameters that we might have selected. So for instance, if we've selected a given epsilon value and a given min points value, what we can do is look up the corresponding k nearest neighbors plot, draw a horizontal line in that k nearest neighbors plot. And what that tells us is that any point with a k nearest neighbor value or a k nearest neighbor distance that is less than or equal to your epsilon will be considered a core point. And any point with a k nearest neighbor distance that is greater than this epsilon could either be a border point or noise point. Okay. All right. Any questions on that? Okay, so let's just go through one exercise. So I'm going to skip over these part A and part B here, and we can just look at question B here. So let's just say, for instance, we wanted to cluster this data set here and assume, again, assume that we can't actually see this data set with our eyes. So assume that we wanted to cluster this data set using dbScan. with a min points value of 3 and a epsilon parameter of square root of 2. So what we would do is look up the following two k nearest neighbors plots. So to start, we would look at the k equals 2 nearest neighbors plot. And then we would draw our horizontal line at square root of 2. So that's this value here. Okay. Okay. And so we can see that 11 points have their k equals 2 nearest neighbor distance less than or equal to square root of 2. And we can see that 2 points have their k equals 2 nearest neighbor distance greater than that epsilon value. Okay, so what that tells me is that based on the k equals 2 nearest neighbors distance plot, this tells me that there are at least 2 noise points. Okay. And then, given that my min points parameter that I've selected is 3, to learn a little bit more about my dbScan clustering, I will look up my k equals 3 nearest neighbors distance plot. And then again, I will draw a horizontal line at the square root of 2. Okay, so that's this right. Oh, no, I'm looking at the wrong thing. It's this right here. Okay. And so what this shows me that there are 5 points whose k equals 3 nearest neighbor distance is less than or equal to that square root of 2. Okay. So what that tells me is that with this dbScan parameters that I've selected, there will be 5 core points. Okay. And so that can give me a sense as to, how many noise points that I might end up having, as well as it'll tell me exactly how many core points that I'm going to end up getting. Now, while the number of core points is not going to exactly tell me how many clusters that I'm going to get, it will give me a sense, for instance, as to, like for instance, like it might be the case that you end up having too many clusters. So for instance, if you have like a ton of core points, if your core points is like close to the size of the data set, you're basically giving your dbScan algorithm no chances to, link up, other points with each other. So you might, for instance, consider, changing your parameters such that you have fewer core points if you find, so if, a situation in which like you might have too many core points might be something in which like, even your noise points end up being core points. So you end up getting like a lot of like these singleton outliers. This can basically be used as a way to learn a little bit more about the nature of your clustering to help you hopefully, select the ideal clustering that you're, looking for in the end. Okay. All right. Any questions on that? Okay. So let's use these insights from the k nearest neighbors plots to cluster one of our actual data sets here. Now, this is not going to be a high dimensional data set that we are clustering in this application here, because I think it's beneficial to go through a lot of these two-dimensional artificial data sets so we can learn a little bit more about what types of results you might end up seeing when you use this dbScan clustering algorithm, and how that can, for instance, like it's going to give us clues as to, for instance, why the dbScan algorithm may or may not work under certain scenarios. So we're actually going to use dbScan to cluster the two data sets that we saw in the slides. So we have this noisy density-based set of clusters here in this noisy data set. So we, based on what we see here with our eyes, we can definitely tell that this is in fact a data set that would be useful for dbScan, because ideally we'd like for dbScan to cluster, the observations that we see here in the dense clusters, and we'd like for these noise points to hopefully be excluded. However, we can't actually, we're going to assume that we can't actually see a data set such as this with our eyes. So we want to rely on just the tools that we have in order to make this assessment as to whether, dbScan is useful, as well as, what min points and epsilon parameters that we should choose essentially. So we'll cluster this data set, and then in addition, we're also going to cluster this very similar data set with the same, cluster shapes, except this data set is not going to have any noise. So it's also a good idea to, examine when it's not useful to use dbScan. Okay. So the first thing that we might want to assess is, not just is dbScan going to be a useful clustering algorithm to use, but is the data set clusterable at all? So we can use our Hopkins statistics for both the noisy data set as well as the not noisy data set. And so based on what we're seeing here, my question for you is, does the Hopkins statistic suggest that this data set is clusterable? Well, actually, I'll say that these data sets are clusterable. All right, so let me launch a poll. All right, so remember, this is the question that we're asking here. Okay, so try submit in the next few seconds. Oh, excuse me. Okay. So slight majority of us say yes. But actually, based on what we're seeing here, with all of our Hopkins statistics that we've calculated for these two data sets, actually what the Hopkins statistic is suggesting is that the data set is in fact not clusterable. So you want to remember, the closer your average Hopkins statistic is to 0, the more clusterable the data set, the more clusterable it is suggesting the data set to be. On the other hand, the closer these average Hopkins statistics are to 0.5, the more unclusterable it's suggesting the data set to be. So basically, both of these Hopkins statistic averages are much closer to 0.5. So what that suggests is that they are not clusterable. So the next question is, why do we think that the Hopkins statistic failed? Based on what we can see with our eyes in these 2D plots, why do we think the Hopkins statistic failed to identify a clustering structure in these data sets? Yeah, so the noise points definitely aren't helping. But we do see, for instance, that even without the noise points, the Hopkins statistic still suggested a average value that is much closer to zero point 0.5. Yes, I'm seeing a couple of direct messages and a couple of group messages. Yeah, so it's not well separated and not convex clusters. So you want to remember the way that the Hopkins statistic measures whether a data set is clusterable or not is based on essentially how many gaps exist within the range of observations in the data set. So the more gaps you have within the window that essentially surrounds the data set, the more clusterable the Hopkins statistic suggests that the data set is. So we can see in these two particular data sets, the window is very tight. The range of values around our data set is actually quite tight around the shapes that are packed in that window. So in other words, there's not a lot of gaps within the range of values surrounding either of these data sets. Okay. I might need to reboot. Sorry about that. Let's see. Come on. Ugh, sorry. All right. The thing that we want to remember is uh, both of these data sets do not have a lot of gaps that exist within the range of data set values. Okay. All right. So unfortunately, the Hopkins statistic was not a useful technique to use to evaluate whether there's a clustering structure in this data set or not. So therefore, this showcases the need to hopefully be able to try out multiple evaluation metrics for attempting to answer the same question. But any questions on that? So let's use one of our other techniques that we discussed for determining whether a data set is clusterable or not. So we'll take our noisy data set first, and we'll put it into a series of TS&E plots. Okay, and so we're not seeing any strong clustering structure yet, but as we increase that perplexity value across multiple random states, we are in fact seeing evidence of a strong clustering structure where quite a few of our clusters are in fact well separated. Perhaps some of them perhaps are not well separated like these here. Now, in addition, we want to remember that, under some scenarios, the TS&E plots are not able to faithfully reflect noise in the data set. So what we see here, is what we would expect, right? We would not expect to see a, field of noise that exists around our density-based clusters. Now, what we saw in previous examples is sometimes the presence of noise will actually lead to the TS&E plot to, create these phantom clusters, if you will, that are comprised of some of our noise points. So now the nice thing in this particular data set is we didn't actually see any evidence of that happening. The noise points, because they were so close to our density-based clusters, luckily did in fact end up getting lumped in with our our actual cluster. So the nice thing is that, in this case, the TS&E plots were not, hallucinating additional clusters that didn't actually exist. But, the downside is, if we did not actually have this, two-dimensional data set that we can see with our eyes, we still would have, we still would be unaware of whether there was or was not any noise points in this data set. So therefore, it is going to be useful to create these k nearest neighbors plots to give us a sense as to whether that noise actually exists. Now, for comparative purposes, we can also put our not noisy data set into our TSNA plots, and we can examine what goes on and what kind of results that we end up getting. Okay, and we do in fact end up seeing very similar shapes showing up in our not noisy data set. So we do see, mostly well-separated clusters, except for these ones here. And we do end up seeing, for the most part, the same shapes of the density-based clusters that we saw in the not noisy, or excuse me, in the noisy data set. So let's first examine our noisy data set. So the first thing that we'd like to determine, is dbScan going to be a useful clustering algorithm to use in the first place? Or in other words, does our data set have noise? And you want to remember that, many of our other clustering algorithms that we've talked about are sensitive to noise. So even if even if you're not sure if you plan on using dbScan or not, looking for noise in your data set can be a useful, preliminary analysis to run. So it can basically give you a sense as to what type of clustering algorithm is going to be more or less useful for this data set. So the way that we can create those k nearest neighbors plots is using the following code. So what I'm doing here, so I'd like to look at a series of k nearest neighbors plots. So for instance, I'd like to look at a k equals 2 nearest neighbors plot, all the way up to a k equals 9 nearest neighbors plot. So I'm going to use this nearest neighbors function, and I'm going to give it the number of neighbors that I'm going to be looking for each observation in the data set. Okay. And I'm going to fit that nearest neighbors function, in this case, with my noisy data set. Okay. So this creates this neighbors object here. And then furthermore, if I want to actually extract the nearest neighbor's distance values for each observation in my data set, I need to use this k neighbors function as well with my same noisy data set. Okay. And so what I'm going to be using to create those nearest neighbors distance plots is the resulting distances matrix, which is going to be a matrix that looks like this, where basically my rows represent the observations in X noisy. And then each column in this distances matrix represents the distance each of these given points are to their k equals 1 nearest neighbor, their k equals 2 nearest neighbor, so on and so forth. So for instance, if I'm looking for my k equals 2 nearest neighbor, what I can do is I can transpose that matrix first, and then I can basically, look up the column, if you will, that corresponds to that k equals 2 nearest neighbor distance. So basically do 1 minus that k value. Okay. And you want to remember that this k nearest neighbors plot needs to be sorted from the smallest distances to the highest distances. So I'll take that sorted nearest neighbor distances, and I will plot it in a line plot. Okay. And so I get my k equals 2 nearest neighbors distance plot, k equals 3, all the way up to k equals 9. Okay. So I can see a very similar set of suggestions in each of these k nearest neighbors distance plots. So for instance, I see for the majority of points in this data set, I see this very gradual incline in the distance a point is from its nearest neighbor. And then basically right at the very end, so basically the final 159 points roughly in this data set, I do see this dramatic jump in the distance a point is from its nearest neighbor. So this might be giving me an indication that number one, my data set does in fact have noise, number one. And number two, if I plan to use the dbScan clustering algorithm, I might be on the lookout for a clustering that roughly returns about 159 noise points. Okay. All right. Ooh, I'm out of breath. Any questions on that? Alrighty. So simply just having a sense as to how many noise points exist in our data set is not really enough to give us the most insightful set of parameters to use in the dbScan clustering algorithm. So what I'm going to do is I'm actually going to plot a variety of different metrics when parameter tuning my dbScan clustering algorithm. So if you want to use the dbScan clustering algorithm, you can use this dbScan function here. Okay. And then when you're instantiating that dbScan object, you can instantiate the epsilon value as well as the min points value. And it's also useful to stipulate the distance metric that you're using. So I'm just going to use Euclidean. All right. And so if I'm using a particular epsilon and min points parameter value, I'll basically first instantiate that dbScan object. And then when I'm ready, I'll use fit predict on my given data set. Okay. And so like I've seen with other scikit-learn functions, the fit part of the fit predict simply just says run the corresponding algorithm. And then if I include the predict part in the fit predict function, what that means is that the scikit-learn function will usually spit out a relevant output based on that algorithm. So in my particular case, what it is returning to me is my set of cluster as well as noise point labels for each of the observations in my data set. Okay. And so to engage in parameter tuning, what I might choose to do is iterate through a series of min point values, as well as iterate through a series of epsilon values. So what this is iterating through, it's a series of epsilon values where my step size, so basically it's going to be a range of epsilon values starting from 5 and then going to 19.5. Yes, this is basically setting the upper bound limit. And then basically each of my step sizes within this range is going to be 0.5. So basically I'm going to iterate through a series of epsilon values that are, going from 5, 5.5, 6, 6.5, so on and so forth, all the way up to 19.5. Okay. And so basically I'm going to try out a series of min points and epsilon values. And for each of these runs of the dbScan algorithm, I'm going to be extracting 3 separate things about that algorithm. So I'm going to be collecting, number one, the number of clusters in the corresponding clustering, the number of noise points, and then also the average silhouette score of the clustering. Okay. Now, the thing here that we want to keep in mind is this is not just any scikit-learn clustering algorithm. So the, if this was basically just k-means, we wouldn't really need to think about what those label values actually are. So scikit, or so DB, the dbScan function, the way that it designates a noise point from a clustered point in the dbScan algorithm is the following. So basically, so if your cluster label, put that in quotes, is specifically set to -1, that means that the observation is a noise point. Okay. And then if your cluster label is equal to any other number, so 0, 1, 2, what that means is that that observation is in the corresponding cluster with this label. Okay, so for instance, if you wanted to create a data set with just your clustered points, and you wanted to filter out the noise points, then you could perform row filtering on that given data frame. So in other words, we're telling this data frame we would only like to keep the observations that correspond to a predicted cluster label that is not equal to -1. Okay. So if you would like to count up the number of clusters, in your clustering, there's a couple ways you could do it, basically. So for instance, you could take that original data frame and, for instance, you can use the value counts function. And basically what this does is it creates a data frame or a Panda series with a distinct, or a row basically that corresponds to each distinct cluster label in this column. And then what you can do is basically simply just take the length of that Pandas series that was created. Now, technically, if your data set had no noise, this would give you the number of distinct cluster labels. But if your data set does have noise, which ours does, then you would want to basically do 1 minus that cluster number, because we know that one of those cluster labels is in fact going to be -1. Okay. So that gives me the cluster numbers that I'm collecting here for each set of parameter values. Okay. And in addition, I might also want to count up the number of noise points in my data set. So in this case, I can use, for instance, row filtering, where in this case, I would want to take my data frame and only filter for those rows whose predicted cluster label is equal to -1, i.e. it's a noise point. And I can simply just calculate the length of that noise point data set. Okay. And so that would be my number of noise points in the data set. All right. And then finally, I also want to calculate the average silhouette score of each of my dbScan clusters that I've created. Okay. So there's going to be a little bit more work involved because we really only want to calculate the average silhouette score of the actual clusters in the data set. So we don't actually want to consider the noise points as its own distinct cluster. So in this case, when calculating your average silhouette score, you only want to do it for the clustered data points. So what that might mean is, if you're using your silhouette score function, which calculates the average silhouette score, you might want to, or you would only want to apply that to your data frame in which you have specifically filtered out your noise points first. Okay. And so what I'm doing here is I'm only calculating the average silhouette score directly if the number of clusters is in fact greater than one. So basically, if you try to calculate the average silhouette score of a clustering with just one cluster, actually that silhouette score function does not work. So basically, if your number of clusters is simply just one, then we actually set our average silhouette score to simply just be a 0, basically. Okay, so we don't really want to consider that clustering. Okay, now there's this additional Kalinsky-Harabasis score that I think we're going to skip over, but it's basically another clustering evaluation metric that can also be used to evaluate the general cohesion and separation of a clustering. In the interest of time, we're going to skip over that. But basically, the result of all of this code gives us the following sets of plots, which indicate to us, sorry. The following information for each set of epsilon and min points parameters that we have tried out. So we are examining for each one of those combination of parameter values, the average silhouette score, the number of noise points, as well as the number of clusters. Okay. Now what we're going to see here is this is going to be a scenario in which we want to be careful not to simply just use one and only one evaluation metric to help us select our best clustering that we might be looking for. Okay. So if you are simply just using the average silhouette score to help you select the ideal DB scan clustering, what parameter values would you end up going with? So question for you all. So here we have our average silhouette score plot where our min points is 2. And these are all our epsilon values. And on the y-axis is our average silhouette score, right? And then here we have the same plot where our min points value is 3. Our epsilon value is on the x-axis, and our average silhouette score is on the y-axis, so on and so forth. So what, if we were just using the average silhouette score to pick the clustering that we're looking for, what min points value would you use and what epsilon value would you use? Are we gearing up for the checking Tuesday? Is that why? Have I lost y'all? So when it comes to using the average silhouette score to select the best clustering, if you recall, generally speaking, the clustering with the highest average silhouette score is considered to be the best, if you will. Yeah. Okay, cool. Thank you. Yeah. So I'm seeing min points of 4 and epsilon is equal to 5. Yeah. So for instance, by looking at all of these average silhouette score plots, so this one, and this one, we do end up seeing the highest absolute average silhouette score with a DB scan clustering of min points is equal to 4 and epsilon is equal to 5. However, why do we think that this particular clustering here is not actually going to be the one that we want to go with? All right. Well, I'm about to check. I'm about to let you guys check your emails, but the bullet point is take a look at the number of noise points and the number of clusters that resulting dbScan clustering would give us, right? So with the epsilon value of 5 and a min points value of 4, we would end up getting like almost 2,000 noise points and about 300 clusters. So based on what we saw in our TS&E plots, we have a strong indication that that is too many noise points and too many clusters. Okay, all right, so I'm going to check my email. And let's see if my checking Tuesday emails have gone out. They have not gone out. Let's see here. Hopefully they're going out soon. Okay, I did set for them to go out at 4:30 today. Why is this not happening? Okay, well, I'll just send them now. Okay. Okay. All right. So the emails have gone out. So I'll give you guys about 30 seconds to check your email to see if you've been one of the people that were selected. And just as a reminder, if you have been selected, you should log off the Zoom meeting link here. And it is your responsibility to watch the remaining 20 minutes of class content.
I'm sorry, I have a question.
Uh-huh.
So there were like 6 or 5 checking Tuesdays already, and I haven't been selected even once.
Mm-hmm. Yeah, so
Is-
we have about 70 people in the class. So not everybody has yet to be checked yet, but you will, you can expect to be checked twice during the class.
Okay, thank you.
Yep. No, it'll happen. I promise. Okay. All right, so I'm going to assume that everybody has had the opportunity to check their emails and whether or not you have been selected. So so let's take a look at how these plots might indicate what type of clustering that we might, or what set of parameters we might want our dbScan clustering algorithm to return to us. So this is another scenario in which simply just relying on the average silhouette score alone to pick out our ideal clustering is ultimately going to fail us, right? So we see that this average silhouette score, while it is the highest out of everything that we've tried so far, it is going to give us a number of noise points and a number of clusters, which we have evidence to suggest is too high. Okay. However, we do end up seeing here for all of these min point parameters is that as we increase that epsilon value, the number of clusters decreases for the most part, as well as the number of noise points. So generally speaking, we only want to be looking at epsilon values that are greater than or equal to 10. Okay, we can see that, if we go back to examining just the epsilon values that are greater than or equal to 10 in our average silhouette score plots, I'm just going to draw a big vertical line here. Not going to let me do that. Then we do end up seeing these peaks in our average silhouette score plots. Okay, so it actually looks like for the, when we're using a min points value of 2 and 3, this peak average silhouette score is actually really low. It's actually a negative average silhouette score. So this is indicating at the very least by using the Euclidean distance metric, this is indicating poor cohesion and separation, if we use these min point values. On the other hand, if we look at, min points of 4 or min points of 5 even, we do see the average silhouette score at these peaks being some of the highest that we've seen for epsilon values that are greater than or equal to 10. So that's going to give us an indication that of how to basically narrow down some of our parameter values that we're looking for. So let's recap what we just said here. We want that epsilon value to be greater than or equal to 10 because when epsilon is less than 10, the number of clusters and noise points is too large. And then we've narrowed it down. So we only want to look at min points of, let's just say 4, because this actually does, in fact, end up being the higher peak in comparison to this one here. So min points is equal to 4 is the best parameter because it has the highest average silhouette score, or dB scan, or when epsilon is greater than or equal to 10. Okay. And so furthermore, so what we might choose to examine is min points of 4 and a range of epsilon values that are around where this average silhouette score peak is occurring. Okay, so let's explore a couple more of these dB scan clustering results. Okay, so what I've just returned is a little bit more information, so the actual data that went into these plots. So for instance, we can see that the actual average silhouette score peak is happening around epsilon values of 13.5 and 4. And unfortunately, while this is the peak, or this is where the peak in the average silhouette score is happening, what this is showing us, what this would give us, is a dB scan result with about between 90 and 93 noise points, which, based on our k-nearest neighbors plots, looks like it might be a little bit too low. And then on top of that, the number of clusters that correspond to the dB scan clustering with these two epsilon values is also too low, based on what our TS&E plot suggests. So let's just look at a range of epsilon values that kind of exist here, between these particular epsilon values here, where roughly that peak was occurring in the plots that we had just looked at. So for visualization purposes, we're going to use our TS&E plot. And we're going to color code our TS&E plot by our cluster labels. So the cluster labels are going to basically be the colors. And then we're also going to color code our noise points with black markers. So we can do that by actually creating 2 scatter plots. So we're going to use 2 scatter plots here. We're going to look at, simply just the X and Y coordinates of our TS&E projected data set. And for our first scatter plot, we're going to color code again by the predicted cluster label. And specifically, we only want to plot the points in the data set whose predicted cluster label is greater than or equal to 1. Or in other words, the non-noise points. Okay. And then in that second scatter plot, we're going to simply just use 1 color. And our data set that we're going to be plotting is going to be just the noise points. Okay. All right, so taking a look at our resulting dbScan clustering results. So each of these is going to correspond to the dbScan clustering with min points of 4 and epsilon of 10. And we're doing epsilon of 10.5. Okay. And so we can see what the plots were suggesting, essentially. So basically, we can see that when our epsilon value is set low enough, we do in fact get a dbScan clustering, which is able to separate each of the TS&E plot suggested clusters that we can see here. But unfortunately, as we increase that epsilon value to 10.5, some of our density-based clusters that we have evidence to suggest should be separate are now, in fact, merging together, or they're being clustered together. And unfortunately, so we could, in fact, we could choose, if we want all of our sets of observations suggested in the TS&E plot to be separate, we could go with this clustering here. But unfortunately, this comes at the expense of having quite a few, sets of observations within each of our density-based clusters be like separated from each other. So here we have a couple of points that broke away here, a couple of points that broke away here. Okay. And so, if we keep that epsilon, if we keep increasing that epsilon value, unfortunately, what we end up seeing is that more of our density-based clusters suggested by the TS&E plot do, in fact, end up being unseparated from each other. Okay. And so, given that we had a suggestion, so given that our TS&E plot suggested that there were, in fact, 8 clusters in the data set, you don't want to simply just rely on the calculations that we plotted above, because basically here we have a clustering with 8 clusters, but unfortunately, these are not necessarily the clusters that we have evidence to believe should be the ones that we are, should be looking for. The 8 clusters, unfortunately, end up manifesting as like these little, some of these points that broke away from the larger, inherent cluster that we would like to be, separating here, if you will. Okay. So I think, what else do I want to say about that? But on the other hand, the nice thing is that we were, in fact, able to identify, and we can, because this is a 2D plot, we can actually check our answers in this case. So the nice thing, though, is that, with this particular clustering here, we were, in fact, able to, detect and throw away, if you will, most of the noise points that did, in fact, exist in the data set. So something to keep in mind. And this actually ends up happening for a lot of the dbScan parameter values that we selected here. Okay. So this would be the set of results that you would want to choose from if you were using dbScan to cluster this noisy data set. Okay. All right. Any questions on that? So based on what we see in this 2-dimensional scatter plot of the original data set, do we have any intuition as to why dbScan was not effective at clustering this particular data set? So why do we think dbScan failed to identify the 8 inherent clusters that we're looking for in this data set? Does anybody want to raise their hand and shout it out? Yeah, so the noise points are too close to the dense groups. Yeah, so it has to do with the separation of these clusters here. Because you want to remember, the way that sets of points are joined in the dbScan algorithm is based on whether the corresponding core points are within the given epsilon radius of each other. So let's just say our epsilon value was set to be like a radius of this. So, and then our min points value was set to be 4. So if that was the case, what that would mean is that this point here would be a core point because it has 4 points within its epsilon radius. And so would this, and so would this. So if our min points value was 4 and our epsilon radius was 11.5, which is roughly about this radius here, then we can see basically that a bridge of connected points unfortunately made it impossible for these two clusters to separate. And so, what we could have done is we could have chosen, for instance, to decrease our epsilon radius. So now in this case, our this point here would not be a core point because it did not have at least 4 points within its epsilon radius. But then the downside of that is, what we were seeing here is that we ended up getting, because this cluster here in particular was more sparse than the other clusters in the data set, what that led to was more of a separation of inherent clusters. So basically, these, unfortunately, sets of points were not able to connect to these sets of points because we set that epsilon radius too low. So basically, this core point might not have linked with this core point, for instance. So this kind of highlights some of the benefits, but also some of the downsides of using dbScan to cluster your data set. So just quickly go over some of those pros and cons here. Come on. No. Hello. Looks like I need a reboot. Sorry about that. Okay, so very quickly, one of the downsides is what we just saw here. So dbScan tends to not work as well when you have clusters that are not well separated, as well as clusters that do not have the same sparsity. So we can get a situation like this, okay? And then another downside that we ended up seeing was that you can't, unfortunately, pre-select the number of clusters that you like. So it does take a little bit of intelligent parameter tuning of your min points and epsilon values to give you the ideal cluster numbers that you might be looking for. Okay. And then on top of that, this is an algorithm that is more computationally complex than k-means. So for instance, in dbScan, we do need to, calculate the distance between each pair of observations in the data set. So basically the act of creating that distance matrix, that m by m distance matrix, does increase the amount of computational time that k-means does not actually have to involve itself in. But dbScan does have some benefits over many of the other clustering algorithms that we've talked about. So, one of the main benefits is that it can, at the same time, identify both clusters and weed out the noise. Okay. Now, another cool thing is that it can also, it's not bound to finding clusters of a particular shape. It's actually technically possible to identify clusters of, any particular shape. So they can be convex, they can be non-convex. And then another potential benefit, you could view this as is that you actually don't have to pre-select the number of clusters that you're looking for. So basically, you don't necessarily have to have a sense as to what that ideal cluster number might be. So just as a recap, very quickly before we leave, we've discussed one other clustering algorithm that can identify clusters of any shape. So what is that clustering algorithm? So after this, I'll call it a day. So you remember TS&E is not an actual clustering algorithm in and of itself. It's a dimensionality reduction algorithm that's used as a visual aid in our cluster analyses. So it's a different actual clustering algorithm. You remember when I was drawing those little spherical clusters? There's one algorithm that could do it. Yeah, so one of our hierarchical agglomerative clustering algorithms can identify non-convex shapes. So which linkage function was it? Not quite. So I'll just tell you. So the cool thing about hierarchical agglomerative clustering with single linkage is that it can also identify clusters of any shape. All right, cool. All right, so we'll wrap there. So we basically finished up with the dbScan clustering algorithm. I wanted to go through one additional example on Thursday in which we're talking about how to essentially perform the same analysis on this data set that does not have any noise. So for instance, how might we know that our data set doesn't have any noise, and how would we go about selecting our dbScan parameters accordingly under that scenario? Okay, cool. So we'll wrap there. I will stop recording.